Okay, small chapter today, chapter 5, which is computers and computer architecture. So digital logic circuits lay the foundation of how computers function in modern electronic devices. All right, computers. First up is computer organization or computer architecture. Typical computer architecture is comprised of a processing unit that is known as a central processing unit. Central processing unit in turn is comprised of a control unit and something known as a ALU. ALU stands for arithmetic logic unit. Okay, so we had our logic gates. Logic gates perform some logical functions, right? AND gate, OR gate, NOT gate. So those functions are basically implemented in the arithmetic logic unit, ALU. So it performs the mathematical operations. And the control unit controls everything, as the name suggests. So control unit with the ALU comprises the CPU, the central processing unit, or the main processor of the system. And then this processor, CPU, interfaces with the outside world. It needs to receive input. There should be a way for us to send information into the processing unit, CPU, and a way for the CPU to actually interface with peripheral units. And those take place via buses. So a bus, which is basically what you see here, a bus is nothing but a bunch of wires. It carries information, it carries data from point A to point B to point C, and so on and so forth. So a CPU needs to interface with the outside world, input devices, as well as the peripheral output devices. Also internally, it needs to interface with memory, with storage, lots of other devices. If you have a smartphone or a tablet, for instance, you might have wireless modems in there, okay? Even in a laptop or a desktop, these computing devices would interface with several different devices. Okay. The size of the bus or the number of wires depends on the application, obviously. So the earliest processors were a 4-bit processors. So it was a 4-bit bus. Then we have 8 bits, 16 bits, and modern electronic devices are now 64 bits. That's the current standard, current consumer standard. Right? That's the current consumer standard. The 64 bits of information going all at once. We can go into the CPU and take a look at how it would interact with everything else. So it's an example of how a CPU interacts with different parts of your computer system or computer system. So here you have the CPU down here, and here you have the CPU bus. The CPU bus is basically, again, as I said, it's a collection of wires. There's a clock that keeps everything in sync. Everything is communicated via the CPU bus. CPU needs to connect with the different memory systems that are present in your computer system. There is RAM, which is random access memory. There is ROM, which is the read-only memory. The nomenclature of these two types of memory is a little weird, okay? So I'll explain. RAM, or random access memory, refers to basically how the memory is accessed by the CPU, okay? So typical access takes place either in a sequence or you can access it randomly. So the memory is stored in a sort of a matrix-like structure, right? You have a matrix-like structure, let's say X and Y. And then each intersection of the X and Y architecture allows you to store one bit of data. So if it's in a sequence, you'd have to go into the matrix, and access it one by one in one step. Meaning if you had, let's say, 64 times 64, a matrix of 64 bits times 64, and if you needed to access something in the middle, you'd have to go step by step to access it. Okay, and this is, again, by far a very simplistic explanation. So that obviously would take up some time, right? Whereas random access, you can go in and you can access whatever you need directly. Will not need to spend any time. Hence the name random access memory. Okay. Now versus read-only memory. Read-only memory does not refer to the type of access. Read-only simply refers to whether the memory is volatile or non-volatile. Okay. Volatile means power must be supplied to the memory for the information to be stored in there. As soon as the power turns off, the data is wiped out. So RAM is actually a volatile memory. ROM, which stands for, again, read-only memory, is non-volatile. So this was in the early days of electronics when they were trying to create these electronic systems. ROM was a very important component. Okay, it still is. When you actually boot up your computing systems today, there is an inbuilt program. That program is known as a firmware. The reason it's known as a firmware is because the memory is stored in a ROM chip. So it's firmly coded into the system. It tells the computer, it tells the CPU what it needs to do when the power is first supplied. Okay, that is also known as the BIOS in the in Windows PCs, basic input-output systems. Anyway, so those programs are stored in the ROM, read-only memory. And to extend read-only memory, we came up with programmable read-only memory, which is what you see here, PROM. It's not the PROM for an EE department. The EE stands for electrically erasable programmable read-only memory. So again, read-only memory, as the name suggests, at the manufacturer's factory, the program is already stored in the ROM chip itself. You cannot program it again. The programmable memory means you buy the ROM chip and you can program it once, hence programmable ROM. Then came the EEPROM, which was the erasable PROM, which was erasable using only a UV light. And then came the electrically erasable PROM, which was EEPROM. That's what the name stands for. Anyway, as consumers, we don't have to worry about any of this, but as engineers, you might come across something like this in your systems. So inside a computing system, probably not, but let's say as mechanical engineers or industrial engineers or biomedical engineers, you would come across an embedded system that does use something like this. Okay, so there might be a time where you would be working as an engineer and you would have a small embedded system inside your larger mechanical system. So again, as I was saying, volatile memory is the RAM. Random access memory is volatile. Then there are multiple classifications: static RAM and dynamic RAM, SRAM and DRAM, non-volatile memory, flash. Of course, nowadays has reached consumer grade. And so we use flash memory in all of our computing systems nowadays, right? Previously, we only had USB flash drives. Now everything is a solid state drive in SSD. On this side, on the right side, it's the more important interfaces. We have the ADC and the DACs. ADCs are basically analog to digital converters, and DACs or DACs are known as digital to analog converters. So oftentimes you would have a system where you would have analog measurements or analog sensors, and those analog sensors will sense some physical quantity, which would then be converted into a digital quantity or a digital signal. Okay, for example, there's an analog sensor right here. There's a microphone. That microphone captures the analog signal, which is the sound from my voice, and converts it into an electrical signal. It is then sent, it is still an analog signal. It's sent into the computing system, where a ADC converter will take that analog signal and convert it into a digital signal. Another kind of sensor is the camera sensor in here. Another sensor is the thermostat on the wall that measures the temperature. Camera sensor would measure the light. Those are still analog signals. Somewhere in there, there would be an ADC converter or ADC, which would convert the analog signals into digital. And that digital signal is then processed, and then it's processed by the CPU, and the output is sent. Now, when the output is sent, that output might need to be converted back into an analog signal. So digital to analog converter would be required for that, right? If you have a digital amplifier, perhaps that digital signal is amplified. And if you want to send that output to a speaker, let's say, you would convert that digital signal back into analog and then send it out. Okay, so you have an A to D converter and you have a D to A converter. And then peripherals, you have sensors, actuators, and peripherals. Sensors could be anything like mics, camera, thermostats, etc. Okay, anything that is being able to sense physically, like any physical quantity that you want to be sensed and interface into your system. So computer systems are hardware which requires some software for it to function. We need to be able to tell the computer system on what it needs to do. So we have computer programs. Computer programs are basically the programs written by humans in a language. But the computers do not understand this language. So there are multiple levels of programming languages. At the lowest level, or what we call the lowest level, is basically machine language, which is the language that machines understand, right? You apply a voltage, the machine understands voltage. You send some current, the machine understands current. It doesn't understand if you type 9 or press 9 on your keyboard, computer doesn't understand. Computer just understands voltage, presence or absence of a voltage. So you have machine language. And then a few steps above machine language, you have assembly language, and then you have compilers, and then you have human language, human level language, which is basically our programming languages that we use in the world today. So higher level languages, basically C, C++, Python is very popular nowadays, very easy to learn. So even as non-CS majors, even EEs, MEs, IEs, it behooves every engineer nowadays to actually learn some sort of, at least have some rudimentary programming skills. Okay. CPU registers basically store data, so it retrieves data and stores results of computations. Now CPUs are monitoring an entire system, right? On the previous slide, we showed how, or we saw how computers, not computers, CPUs interface with the outside world. Now, when you have multiple such peripherals and sensors connected to a system, how does the CPU, or how does the processor know what sensor it needs to react to? It does that in two ways. One is known as polling. The other one is known as interrupt. Polling is where a processor will continuously monitor every sensor that is connected to it. An interrupt is where a sensor or a peripheral will interrupt the CPU and say, okay, hey, I need this. I need your immediate attention. You need to address this. So the CPU is interrupted by its work, and that's known as a interrupt. And so interrupt is very common in higher level computing, meaning all the computing that we do nowadays, whereas polling is used in some sort of embedded system, inside your microwave, perhaps inside your washer, inside your dryer, inside any appliance that just needs minimum functions, not a full-scale computer. Okay, so that's interrupt. That allows the CPU to actually function. And then we have microcontrollers. So microcontrollers are basically a smaller or compact computing system which integrates lots of, not lots of, but microcontrollers can integrate CPU, memory, plus storage, all inside one chip. In a higher level computer, the memory and the storage would be external to the CPU, whereas in a microcontroller, everything would be integrated on one chip. Okay, so again, the purpose of a microcontroller is specific to an application, similar to like embedded systems, like our smart appliances nowadays. Well, not smart appliances, appliances that we had in the past. Nowadays, even the processor inside our appliances, they call them like smart appliances. So they are much more than a microcontroller. Okay. One of the most popular microcontrollers is this chip, ATmega 328P. Okay. It is a reduced instruction set computer known as RISC, R-I-S-C. It's about 28 pin, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 10. Yep, 14. So 28 pin microcontroller. It has two 8-bit and one 7-bit bidirectional I/O ports. So you can interface, you can send commands into it, and you can interface multiple sensors to either send data into it or extract data. Okay. How many of you have used this before? Some of you probably have. Have you ever worked with an Arduino? That's the chip that powers the Arduino. So the Arduino project was an open source prototyping project that was created in Italy. And as good inventions, like all good inventions, this was a meeting of a couple of people in a pub over a few rounds of beers, or a few pitchers of beers, I would say. And they were thinking about how to bring, generate interest in programming and computer hardware and computer software amongst kids and enthusiasts. Okay, so they came up with this project based on. They came up with this controller board based on the chip, the AT328 chip, and they named it after an Italian king known as King Arduin, A-R-D-U-I-N. At least so the story. At least that's the story that I've read. So again, it's a very easy way for enthusiasts, for students, for engineers, for even non-engineers to learn about programming and using some hardware and software to create various different applications. So it hides many of the complex details of working with a microprocessor. It has some built-in memory. It has built-in I/O ports. It can interface a wide variety of sensors. You can buy these kits that are ready-made. and it incorporates many of the sensors. For about $50, you can get like 50 different projects. Okay. One of the, well, that's on the next page. But I'm going to say there's a huge community out there worldwide that creates projects based on this Arduino microcontroller. So there's a large library of high-level functions available. You can simply download them, implement it without knowing any programming language whatsoever, and just build your own project. These user programs are written in C or C++. But again, as I said, there are many programs that are available out there. You can simply copy paste and start learning that way. So here's the time when I was teaching this during the pandemic, and we used this to teach students 251. So in their own homes, they could sit with an Arduino, and with a handheld multimeter, they could do the entire 251 course sitting at home. And one of the things we created was use it as a voltmeter and use it as a humidity and temperature sensor, which is not very difficult. There is a humidity and temperature sensor that comes packaged in that kit. And all you got to do is you interface it with the right pins, take the program, and modify the program to just interface with the pins that you have set, and it can measure humidity and temperature. I have a working model sitting in my office. I had like multiple Arduinos, and so one of them is dedicated to measuring temperature. So again, it sits on my office desk. All right, we're almost out of time. There's 2 slides left, so I'm gonna just continue with that. Then there's the Raspberry Pi. It's much more than a microcontroller. It's actually a microcomputer. That's what I like to call it. So again, there's a huge community of enthusiasts out there. Raspberry Pi is a very popular device. Okay, very, very popular device. And again, it's a microcomputer by itself. And as you can see, but you do need to know some programming to actually start using something like a Raspberry Pi. All right, and then we have a system on a chip, which is what we use nowadays inside every smartphones or tablets. A system on a chip basically incorporates pretty much everything that you need to run an entire computing system. Okay, system on a chip is basically a CPU, has memory, it has modems, it has sensors, it has lots of things that can be integrated on one chip itself. SoCs, as they are said nowadays, made by all these corporations, but all of these designs are licensed by one single company, and that one single company is ARM, ARM. If you need to leave, you can leave. It's already 1 o'clock. I'm just gonna finish talking about this a little bit. So there are 4 primary types of instruction sets. And there was the von Neumann architecture, there's a Harvard architecture, then there's the x86, which was licensed, created by Intel. And then there's something known as RISC, or the ARM architecture, which is ARM. It was a small British company. It stands for Advanced RISC Machines. And now it's become a really big company because this is the only company in the world that licenses their architecture, which is actually used by all the companies in the world. So NVIDIA, Apple, Qualcomm, Samsung, any company that's building their chips nowadays is running on ARM architecture. So if you wish to buy any stock, this is the stock you want to buy. I mean, I'm not recommending anything, but I'm saying check it out, okay? So none of these companies are building, well, they're building their own chips, but the designs come from ARM. Okay. All right. So that was a quick overview of chapter 5, basically computers. And that's about it for chapter 5. Going forward, we are just going to look at circuit analysis for diodes, BJTs, a little bit of FETs, but lots of practice problems. Okay. All right. So we'll end class here today. I'll see you here on Wednesday.